First and foremost, let's offer our gratitude to Almighty God for His blessings so we all could gather here in a perfect condition. Let's start our webinar with prayer. Prayer starts.
So now I can share my screen, right?
Mm.
Okay, thank you.
Yes.
So can you see my screen?
Yes, we can. Yes.
Make this as a presentation mode.
Okay, we just start.
Yes.
Yes. Okay, let's start with the talk.
Yes. So hello, and thanks for having me here. And thanks, Okta, for this opportunity to give you an online presentation of my ongoing work. So my name is Unmi Kim, and I'm a Swiss National Science Foundation postdoc mobility fellow visiting at the Climate and Global Dynamic Laboratory at NCAR in the United States. So today's presentation would be about an ongoing work, which is about potential links between precipitation intermittency and soil moisture variability. And this work has been collaborated with Dr. Ayla Simpson, Clara Desser, Danielle Kennedy, and Flavio Leonard at NCAR and at Cornell. Sorry. So this will be the outline of today's talk. So I will give you a motivation, giving you an introduction to the topic and our proposed research question. Then obviously I will describe which kind of data set we use for our research and methodology and statistical techniques that we apply to this data set. Then there will be some follow-up slide, just few slides showing the result that we got from this ongoing work. So to start, we all know that the atmosphere and land are tightly coupled, influencing each other through different like water masses and surface fluxes. And in long term, the surface moisture, not the surface, actually soil moisture variability is regulated by the incoming precipitation, which is expressed here as P, and evapotranspiration and runoff, which is this Q. So the balance between these three variables is what determines the variability of the soil moisture. But this is an approximation for a long term. And when we consider a amount of precipitation accumulated for a certain period. But we know that precipitation itself in a shorter time period, for example, in a shorter time period or in a daily time scale is not a continuous variable like temperature. Precipitation is rather a discrete climate variable which has intermittent characteristic. And this is a core characteristic of precipitation that makes more complicated to study the overall variability and the distribution of precipitation. In the first plot here, can everybody see my mouse there? Okta,
Yes.
can you see my mouse?
Yes.
Okay.
Good.
So the first plot here is showing the distribution of daily precipitation during the winter period in some year in the central US. Here we clearly can see that there are days with high precipitation and there are some other days that we don't have any precipitation. And this distribution of daily precipitation is what we called as a precipitation intermittency distribution or distribution of precipitation intermittency. And this distribution is also related to the intensity of extreme precipitation. So now, future climate projections given by the summarized in IPCC report, the last one, indicates that in the future climate scenario, we are expected to have an increase in the intensity of daily precipitation. This means that there would be a change in precipitation variability. So in one paper, Tremble in his paper in 2011, described this change in precipitation variability in one sentence, which is it never rains, but it pours. This means that we would have an increase in dry days at the same time increase in intensity of extreme rainfall, which is reflected to an amplification of the dry period and extreme rainfall fluctuation, which indicates high distribution of precipitation intermittency. Now, the question is how this variability of precipitation intermittency is associated with the variability of soil moisture, and this is relatively less explored at the moment. So now to give you somehow visual example of our proposed research question, we can assume two hypothetical cases with two different seasons with different precipitation intermittency condition. For example, we have one case with let's say we have one period with a certain amount of precipitation, but in that case we have precipitation falling evenly across all days of that season. And in that case, it would be the situation with low precipitation intermittency. And on the other hand, we can assume another case that we have exactly the same amount of precipitation compared to the first case, but in this case, this whole amount of precipitation is just falls in 3 days of the entire season, for example, and the rest of the period is just dry. In this case, would be the situation with high intermittency precipitation. In both cases, we know that the amount of precipitation is same, but when we don't know what happened with evapotranspiration and runoff in these different cases with precipitation intermittency, and how these differences will be reflected in the variability of soil moisture. So basically our research tried to quantify this association. So now trying to organize this in a better way, or research question, the proposed question is, how do changes in precipitation intermittency influence soil moisture variability on a seasonal scale? So the focus is not annual, but just seasonal. And then we perform global analysis to quantify the association between these two variables and how the variables associated with terrestrial water balance explain this association. We apply this method in different data sets, and then we also try to understand whether there are some differences between different data sets in representing this precipitation intermittency and soil moisture variability. So the data set that we use is the study period is from 1981 to 2020. And we use some observational data set, mainly two sets of observational data set from Era 5 and Era 5 land. And another set of data set is MS Web for the atmospheric variables and GLIM for the land variables. And we use one simulation, not one simulation, but set of simulation from the climate model, which is the Community Earth System Model 2, a large ensemble project. This is ensemble project that is composed of 100 ensemble members. And the period that we use from this CSM model is from 1981 to 2014, during the historical period. And to complete the rest of the period, we take the period from the SSP 3, so 7.0 climate scenario until 2020. Then the last simulation that we use is from trendy simulation. Trendy simulation is only land model output from the community land model. And this community land model is the land component of the CSM model. In case of trendy, it's uncoupled to the atmosphere, but it's forced with the observational-based precipitation. Not observational-based, but reanalysis-based precipitation. And this simulation was run at NCAR by Daniel Kennedy. And from all these data sets, we take two variables. And the one is the surface soil moisture anomalies at the upper 10 centimeters. So we are taking the surface level. And the another variable is the daily precipitation. So with the daily precipitation, we calculate an index to quantify precipitation intermittency. So for the precipitation intermittency index, we use first another index called number of wet days or wet day index. And this wet day index is based from this paper from Pendergrass and Nuti. And what it basically shows is the number of days that one region takes to have 50% of the precipitation of a certain period. In our case, would be one season. So probably I don't need to give you a detail about that. Just what we try to do is like we have one season, then we calculate the cumulative precipitation distribution. And from that distribution, we try to get the days when we have exactly the 50% of cumulative precipitation. And then we get these wet day values. Then we apply this for each of the season. Then we get wet days for all the period and all the season. And then we calculate the anomalies of these wet days. With these anomalies of wet days, then is multiplied by -1. This is to flip the sign. And this flip sign anomaly is our precipitation intermittency index. So simply you can like remember that negative precipitation index or low precipitation index indicates low precipitation intermittency, and positive precipitation intermittency index indicates high intermittency situation. So, and about the methodology that we use to quantify the association between precipitation intermittency index and soil moisture anomalies, we apply the regression analysis. This involves two-step regression analysis, but so in the first step, I will just try to be fast because this part is also very technical or statistical, and it involves other different tests also. But summarizing what we did is, first we have the effect of precipitation intermittency index and soil moisture anomalies, but we need to extract this effect of mean precipitation from each of the variables, because otherwise when there is indirect common drivers that affect both of the variable, the regression coefficients are not very clear or not very exact. So from the precipitation intermittency, we extract the effect of mean precipitation, and we repeat that for the soil moisture. From the soil moisture, we extract the influence of mean precipitation. Then in the end, we remain with the residual of precipitation intermittency and residual of soil moisture. And in the last step, we apply the regression analysis between these residual of precipitation intermittency and residual of soil moisture. That's what you observe basically here. Then in this regression analysis, what we obtain is the regression coefficient, which shows the direction and the magnitude of the association between precipitation intermittency and soil moisture. And this C is basically what we use to quantify the global association between these two variables. So when this C, so regression coefficients between these two variables, are negative, that indicates that the increase in precipitation intermittency would induce decrease in soil moisture, and also vice versa. A low precipitation intermittency is inducing an increase in soil moisture. And in case of positive regression coefficient, high precipitation intermittency is inducing increase in soil moisture. So direct relationship and vice versa. And from now on, probably I will just, when I mention about this regression coefficient, I will be calling it C, or association between PI and SM. So now showing some of the results here. So this is the global picture that showing the association between the PI and SM, so precipitation intermittency and soil moisture in era 5 in the first column and MS web gleam in the second column. And the first row is for the DJF and the second row is for the JJA. I know the seasonal division works more like for the mid-latitude, and probably this is not real for example, in Indonesia, but this was somehow to see one way to see how these regression coefficients change with the season or with the time, I mean, of the year. So at first glance, what we can see is that there are dominantly bluish, which indicates that regression coefficients are mostly negative across the globe. That negative correlation is indicating that an increase in precipitation intermittency is associated with a decrease in soil moisture. And there are some regions where we clearly see some with high association of PI and SM than other regions. For example, we have here in central US, also in both regions, both data set during DJF, and in case of JJA would be over South America here, slightly here, and Indian Peninsula in this region. At the same time, another difference would be that there are some differences between one data set and another in representing in the magnitude of this association and also the spatial distribution. For example, this number is indicating how many grid points are showing the significant negative regression coefficients, and then we can see that in era 5 is clearly showing higher, like significant association than MS Web Gleam does. But still, the spatial pattern, there are some consistency between these two data sets, and the regression coefficient change with the season. It's quite different from not quite different, but there are some differences between DJF and JJA. So now the next question would be, so they are mostly negative, and what does this mean? What is driving to this negative association? And for that, we can try to see each of the variables that are involved in terrestrial water balance, which means evapotranspiration and runoff. So this plot is showing basically how the anomalies of, let's concentrating in the first one, how the anomalies of soil moisture are like distributed across different values of the mean precipitation and mean precipitation intermittency. So in x-axis, we have the mean precipitation, the percentile of the mean precipitation, so toward the 100 means it's wetter condition, and in y-axis here we have the percentile of precipitation intermittency, and toward higher values indicates high precipitation intermittency. This is values aggregated for all season, for all region. And but taking only the region where the association between PI and SM are negative. And this first one is then showing the distribution for the soil moisture. The second one is for the evapotranspiration, and the third one is the effect distribution of runoff. And when we see the soil moisture, it's basically what we were seeing before, that with high precipitation intermittency, soil moisture tend to be negative. And this is what we also observe with the evapotranspiration anomalies, which means that evapotranspiration is basically controlled by the variability of soil moisture. But the difference that we see is in the runoff. Like we clearly see that runoff in a not in a very dry condition that we see here, but when there are a little bit of a wet situation or more than normal situation, the runoff tend to increase with the increase in precipitation intermittency. That indicates that the desiccation of soil moisture at surface level during the high intermittency period is mainly induced by the increase in runoff. Now, knowing that runoff is the main driver of the soil moisture desiccation with the change in precipitation intermittency. The question is whether this runoff is also a controlling factor in determining the spatial pattern of the association of PI and SM. Then what we can do is quantify the influence of precipitation intermittency in runoff, which is shown in this first plot here. And the below is the regression coefficient that I showed you in the beginning of the result. So during the summer period, we can compare these two patterns. Then we see at some degree that over the region where we see high regression coefficient between precipitation intermittency and soil moisture, we tend to have also high influence of PI on runoff. Over this region in South America, also African region here, and India over here that we observe. So so in this case, with this one, we can see that at some part this is consistent with the spatial influence of PI on Q in runoff, but at the same time, we observe that that's not always true in some of the region. For example, this Amazonian region here, we don't see even the runoff is very influenced by the change in PI. This is not very notable in the notice in the regression coefficient, which is almost like 0. This is happening because over some specific region across the globe, soil moisture is not controlling factor for the terrestrial, for some variables related to the terrestrial water balance, which means that soil moisture is not directly coupled to the atmosphere. Over those regions, for example, in this region, like it would be this region here, in this region, the soil moisture showed negative correlation or regression to the evapotranspiration. This means that increasing soil moisture doesn't affect evapotranspiration, therefore coupling between atmosphere and land is basically inverse or not very significant. This happened because over this region in Amazon and also over this Southeast Asia, this part specifically over here, the soil moisture is also controlled by other factors. For example, the vegetation can pump more like soil moisture over this region. And also there are more like complex river system there, water like storage system there, which like makes soil moisture quite independent from the atmosphere. And that over that region, we clearly don't see very strong regression coefficient and a strong like PI and SM association. And I also forgot to mention that over extremely dry region, for example, would be in that Saharan region and Arabian Peninsula here, we also don't see very strong like PI and SM association. This is because basically there is no precipitation and not strong variability in soil moisture. So that's what basically about the observational data set. Then now, if we wanted to see whether this influence of runoff and also this association between PI and SM is also similarly visible in different models output, mainly the CSM model output. So the first plot here is also showing the association between PI and SM. In CSM model, this is the ensemble of 100 ensemble members. And this is, I'm sorry, this is not the ensemble. This is the ensemble mean of the 100 ensemble members. So we see that overall bluish again, and the spatial pattern looks quite similar to what we saw before with those from the era 5. However, when we make the difference between these association from era 5 to those if we make a difference between the regression coefficient in CSM, which is this one, to era 5, we see here that the era 5 tend to show higher negative values than CSM, so more negative values than CSM, which indicating that CSM show more like reduced association between PI and SM compared to era 5. Then we repeat that with the trendy simulation, so land-only simulation here. And for trendy, this like association between PI and SM is much more complicated, and it's much not very uniform across the region. And when we again calculate the difference against era 5, trendy show much more reduced values of association of between PI and SM. But as I mentioned in the first, like when I explain about the data set that we use, trendy is a land simulation forced with a reanalysis data set, reanalysis precipitation. That means that trendy has a quite realistic data set, the precipitation distribution comparable to era 5. So by having this, that trendy is showing very different spatial pattern. To era 5, this is one indication that precipitation distribution is not the main cause of this model and observation-based dataset discrepancy in representing the association between PI and SM. Then now to try to understand why we see some large differences in this representing the association, we can repeat the same analysis with the distribution of runoff across percentile of precipitation and precipitation intermittency with CSM here and trendy here. Then this plot is clearly different, like how the runoff behave under high precipitation. For CSM, we don't see very specific pattern. It's quite random, except for this like high precipitation intermittency cases, very extremely high precipitation intermittency that we see slight increases. But in case of trendy, it's showing completely opposite case, like to era 5 distribution is. So runoff is decreasing in a situation with high precipitation intermittency. This indicates that in this model, probably PI is not necessarily like affecting changes in runoff. So to understand why this is happening, we calculated something called sensitivity of runoff to precipitation intermittency. So this is basically, in a simplified way, this would be the ratio between anomalies of precipitation intermittency and anomalies of it's opposite. Anomalies of runoff and anomalies of precipitation intermittency. So it's quantifying how much runoff would change with the 1% of change in precipitation intermittency. And then we calculate this value. Then here I'm showing only for the JJA, the global mean of this sensitivity of Q runoff to precipitation intermittency. And here we clearly see that there are like some differences between these three data sets. Era 5 is the one that is showing higher values, which indicates that the runoff in era 5 is gonna respond more like strongly to the change in precipitation intermittency. So CSM is next, and trendy is basically showing very reduced values. But this is only for the JJA, but it's also observed in other like seasons. So these numbers and this like difference in the distribution of runoff is indicating that there are like differences in sensitivity of runoff to PI across different climate model and observational data set. So now giving you a concluding remark, we found that precipitation intermittency and soil moisture association are dominantly negative across the globe, and this association vary with the season. Negative regression coefficients or negative association means that high precipitation intermittency induce soil moisture dryness. And this association would be explained by the increase in runoff when PI increases precipitation intermittency. And we found that there are large discrepancies in PI and SM association between different data sets. And mostly the CSM and CLM, which is trendy simulation, and show much reduced association. And this is due to the weak runoff sensitivity to PI, which is present in this model. And this difference in runoff sensitivity across different datasets and land surface model can have potential impact when we want to make projection in the future soil moisture dryness when this dryness is mainly caused by increase in runoff. Okay, that's all from my side, and thank you very much for your attention. And if you have any question, I will be very happy to receive some.
Okay, thank you, Wunmi, for the great presentation. So it is actually not actually new for me, like the precipitation intermittency for the soil moisture variability here, I think. So is there any question from the participants of this presentation before we continue the session? Okay. Is there any question before? Actually, I have one question actually. Okay, so I'm still confused between the influence of the precipitation intermittency with the runoff. So is the precipitation intermittency the influence the runoff like with a high correlation? Because I think runoff also influenced by vegetation.
Yes, that's sorry, continue.
Yeah, and I also see that in the some part of the world where the correlation is low, it has like a high vegetation covering, I think. So can you explain maybe the process?
Yes, that's basically what that's very good, nice question. Thank you, Okta. And that's basically what I was also mentioning here over the Amazonian region. This is highly vegetated region and where there are some different kind of vegetation here. And then here you can see that still the influence of change in PI can influence quite highly to this runoff, but at the same time, the association between PI and soil moisture is not very strong. And we assume that this is partially because of vegetation. Also, there are also different kind of water storage over this region, but that is vegetation. And then I think I already forgot what is your first part of the question. But we are not exactly, so we know that some region that we don't see very strong connection could be because of vegetation, but we are actually seeing not like explicitly including vegetation itself. So it's more like runoff, assuming all the surface, and then precipitation intermittency as an incoming variable. Yes, but that's something that we need to have a look more into detail.
Yeah, I think so. Okay, we have two questions here. First from Nastiti Andini. She asked, good morning, Miss Kim. I'm sorry, I just joined the presentation. Did you also do comparison ESA, CCI soil moisture data?
Oh, yes, that's a very sharp question. Thank you. And we try to use that data set because it's a direct satellite data set, and that's always good that we use observational based data set first before jumping to like reanalysis or other kind of data set. I think the problem of ESA was that this has relatively low spatial coverage. So before, like, I think before 1990 or something, it almost covered nothing. So that's why we didn't include this data set in the end. But I think ESA CCI is somehow assimilated with GLIM dataset. So GLIM dataset also use different satellite based like product to produce their soil moisture data set. So we didn't use ESA directly, but somehow ESA would be somewhere present in our data set that we use. Yeah.
Okay, so indirectly present then.
Yes.
Okay. Then for the second question from Mr. Dodo Gunawan. Thank you for the interesting presentation. I'm interested in the Indonesian region. What is the form of intermittent rainfall in Indonesia, and when, in which month mostly it happened?
Yeah, we at the moment we are trying to have a more like global picture and identify like regions with strong like connection between precipitation intermittency and low, and a region without a strong connection. So I haven't looked like particularly over Indonesia, but you can see slightly over here when we extend. Indonesia in general is showing quite like good connection, like statistically significant connection between soil moisture and precipitation intermittency. Yes, so that region would be also interesting to see, like in terms of how this tropical region is gonna be like responding to this change, but I can do that at some point. But at the moment, I would say that I don't know exactly how that look like over tropical region, including Indonesia. So,
Yeah. Okay. Next question, the third one from Mr. Ki Agus Ardi Sulistiawan. Thanks for the beautiful presentation. I want to ask for the data. Are you utilize CMIP5 or CMIP6 data for the SSP 370, and any requirements for using SSP 370 on the other hand, and we are able to use another SSPs? Maybe what he want to ask, why are you using SSP 370? Is it
yes,
a possibility?
Yes, also whether I use CMIP5 or CMIP6. So I'm not taking simulation exactly, which is a part of the CMIP5 or CMIP6. I'm using this like set of simulation, which is the CSM Lens 2 project, which is more like a large ensemble simulation project, which they try to produce as much as ensemble member possible. And this one has 100 ensemble members. And I would say CSM2 is a part of the CMIP6. So this is CMIP6 model, but simulation itself is not a part of the CMIP6 as far as I know. But this simulation is like, I think it's open access to everyone. So if somebody wants to see like 100 members, want to use large ensemble member simulation, this CSM2 lens simulation is definitely a good thing to test. And the next one is why I use SSP 3.70. And one reason is that this CSM Lens project with 100 members was only run using the SSP 3.370. So I didn't have any choice to use another SSP scenarios for using this simulation. But at the same time, we are assuming that SSP 3.370 is more realistic future climate scenario. We say, I think there are papers mentioning that probably 8.5 is too aggressive and other simulation are too hopeful. So yeah, that would be the reason.
Yes, it's more realistic. And also, it is interesting to see the maps where when the season of DGF has more positive value on the regression coefficient, yes, over there. But for the GGA, it's overall almost everywhere is blue.
Yes, we assume that actually this high region, what is contributing to more like this bluish region over here. This is because we started having much more variability of soil moisture and at the same time like precipitation. So that's when this region is the melting season, then we started having, and this is basically frozen during the DJF, then we start having some more variability that we can get more significant like relationship. But at the same time, I don't think this region is very reliable in terms of the data set, because when we use MS Web here, it's basically gone. It's not very significant. So probably it's not a good idea to take these high region values. And JJ, in case of Southern Hemisphere, I think, yeah, it's still the same. There are several regions which are always negative, always like significantly negative over this region. Yes.
Okay, so the frozen soil also influence the results then. Okay. Also Miss Nastiti also say thank you for you. And she said, I'm now doing my thesis about soil moisture drought. May I contact you for more information later?
Oh, yes, of course. I would be happy if you do that. So you can find my email here. It's expanded. So otherwise, you can ask Okta for like my contact information. So I'll be always happy to discuss about my research and like your research and interests.
Okay. And my last question, one minute. We already know that there are several types of soil.
Yes.
So is there any influence in the type of the soils and also the correlation between the precipitation intermittency and the soil moisture?
There will be definitely for sure some influence, because runoff, how the rate of runoff is very dependent on the type of soil too.
Okay, so it's already included in the model.
Already included somehow in this regression coefficient, but we are not explicitly again like seeing that effect. Okay. I'm sure that in runoff there are so many factors that influence the mostly related to soil. So yes, vegetation, and also, as you say, soil type, and also the inclination of the surface, topography. So it's quite interesting topic and more like many things to consider.
Okay. And also one last question from the participants. Thank you, Ms. Wunmi. It's a very interesting presentation. Is there any relationship between the precipitation intermittent index and other precipitation index, such as standardized precipitation index that usually used in the WMO? So is there any difference or any correlation between the two of them?
So that could be, I think that means by like standardized drought index could be, or some like extreme weather, extreme climate index. So with standardized drought index could be related. I'm thinking, so yeah, there could be anyway somehow relation between these different precipitation indices, because as the way, when we see the way that this is defining, this is based on the number of wet days, this precipitation intermittency index. And in general, number of wet day index tend to be large when we have more precipitation. Or when also when precipitation intermittency index tend to be low. Wet day index tend to be low when we have low precipitation index. So this pre-index situation is directly related to the amount of precipitation, which means that other standardized index based on precipitation will be also related to that. And that means that we need to remove the effect of precipitation to avoid this effect of precipitation intermittency, precipitation influence on precipitation intermittency index. And that's why when we apply the regression analysis, we basically remove the effect of precipitation. But that's a very good question, that many indexes which is using precipitation, they are quite highly related in terms of the variability and also the values. So when we don't remove the effect of this mean precipitation, all the variables somehow will be related. Yes.
Okay. Okay. Is there any other question? Maybe. Okay. Okay. I think the question and answer session is already enough. the last question is from the participant already answered. So I think I will just give a concluding remark for the presentation before we close the presentation, right? Or do you have anything to add before I close the presentation, Oni?
Well, no, I think I'm done. So if you have some more question or some if you want to know a little bit more about the method, feel free to contact me. And I want to thank Okta again for inviting me and for today's presentation.
Okay, thank you for your presentation, Oni. This is the new research question for me now because I'm also curious about the soil moisture in Indonesia and its relationship with the precipitation intermittency. Because here in our regions, usually the variability of the precipitation intermittency would be varied greatly because of the variability from the El Nino and other atmospheric and ocean relationship as well. So I think it will be more research on that. And I think for this presentation, we found out that there is a relationship between the precipitation intermittency and the soil moisture condition, like the negative precipitation intermittency decreased the soil moisture condition and vice versa as well. And we also have the process of the runoff that might have become the connecting link between the two, between the rainfall and also for the soil moisture. And also there are some other factors that we need to see, to put attention to, such as the frozen soil, vegetation, and also the soil type maybe. Okay, that's all for the talk for the today. Thank you for your attention. Thank you, Wunmi, Kim, for your great presentation and for the time to explain everything of your research here. I'm really grateful for that. And also thank you for the all participants that already give attention and also ask many questions about this topic. And that's all. Thank you very much. Good morning for people in Indonesia and good evening for Wunmi in USA. Okay, thank you very much. And we can clap for the end of the presentation. Okay. Okay, I think that's all. We can close the presentation now.
Okay, bye everyone. Have a good evening, good morning.
Okay, goodbye everyone. Thank you very much for the presentation and also for the attention here. Bye-bye. Okay, MC, you can have the closing remarks as well.
All right. Thank you, Dr. Umi Kim, for the amazing talks. And thank you, Ms. Desa Putu Oktavian Feanti MSG, for leading this amazing session today. All right. And that's a wrap for this webinar. We are grateful for your time and attention given in this webinar. On behalf of our committee, may I apologize for any mistake that has been made. Once again, thank you and good morning for everyone.
Thanks, and also for the information, the recording for this presentation will be uploaded in YouTube. I will share you the link afterward after we upload everything. Thank you very much.